This is Precalculus Chapter 5, Lesson 3, Applications of Exponential Functions on page 345. All right, so we've talked a lot about exponential functions. That is, x increases, y increases exponentially. So your x is in the exponent of the function. Now we're going to give some practical examples. So we did this in Algebra 2. If I deposit money into a bank, I earn interest. And that interest can be compounded at different intervals. So I could have interest compounded every year. That means I deposit $100 at the beginning of the year. I go all year. I'm earning a rate. They only give me credit for the interest at the end of the year. Boom. I get the money. Let's say I have $100. I earn $1 at the end of the year. Then the second year, I'm earning interest on $101. Right? That's compounding interest. That's annual. If it's monthly, then I deposit the $100 on January 1, on January 31st. They give me some money in interest based on whatever my rate is, but the rates always come in an annual rate. So you have to convert that rate to a monthly rate. And you do that by dividing the rate in decimal form by 12, by your compounding period. If it's monthly, it's 12. If it's quarterly, it's 4. There's 4 quarters in a year. If it is daily, then you divide by 365. All right, so we're going to take example 1, and we're going to compound annually. Annually, that's once a year. We'll compound quarterly. We'll go weekly, and then daily. All right, so the formula for earning some rate, or even for bacteria, as bacteria is growing, is the amount over some period of time equals the original amount, or your principal. We use the word principal when we're talking about money, times 1 plus the rate raised to the time. All right, the rate is always in an annual rate. So you'll see if we do quarterly, weekly, or daily, we must make that rate a quarterly, weekly, daily rate, and we must make our times either how many months, how many quarters, how many days, all right? So I'm going to alter problem 1 a little bit because it says for 10 years. So we're going to say we have $6,000. That's my principal. Remember, the amount over time is P times 1 plus R raised to T. So my P value is that $6,000. 8% is the rate, but we always write it as a decimal. And we're going to compound it annually, quarterly, weekly, daily. And I'm going to use 2 years. 2 years. 2 years. All right, so annually, the amount after 2 years would be 6,000 times 1 plus 0.08. 8%. All right, and I'll do that in my calculator. 6,000 times 1.08. I just added those, and I'm going to square that. And I would have $6,998.40. All right, quarterly, so the amount is not after 2 years. It is 2 years, but how many quarters is it? So there's 4 in a year, so 4 times 2 is 8, so it's after 8 quarters, equals 6,000 times 1 plus 0.08 raised to the 8 quarters. All right, you see? Wait, it's not right. It's 1 plus 0.08. That's an annual rate. I have to make it a quarterly rate, so I divide it by 4 because I'm going to earn 1/4 of that each period, right? Or it's an annual rate, and then I'm going to raise it to the 8th. All right, so I'm going to do that in my calculator. 6,000 times 1 plus 0.08 divided by 4. I'm raising that to the 8th power. And I'm going to have $7,029.96. All right, so a little bit more because my compounding period is a little bit smaller. So that what happens is after the first quarter, I begin earning interest on that interest that's deposited in my account at the end of that first quarter. All right, weekly, moving it over a little bit. There are 52 weeks in a year. All right, so I have to make this rate a weekly rate, and I have to make my time. So 52 weeks in the year times 2 years. So this is the amount over 104 weeks, or 104 weeks in 2 years, equals 6,000 times 1 plus 0.08 divided by 52 weeks. And I'm going to raise it to the 104th. So after 2 years, putting that in my calculator, 1 plus 0.08 divided by 52, raised to the 104, I have $7,040.20. Now let's look at it if it were daily. So daily, there's 365 days in a year. So in 2 years, there's 730 days. So the amount over 730 days is going to be that 6,000 times 1 plus 0.08 divided by, I need to make this a daily rate, so I'm dividing it by 365 days, but I'm going to raise it to 730 days. All right, putting that in my calculator. 1 plus 0.08 divided by 365, raised to the 730. This is 7040.94. Not a whole lot different from my weekly. What happens is, as the compounding period gets a smaller and smaller increment, let's say seconds, the value that this approaches is the value of E. If you look on page, let me get there. If you look on page 348, let's just say your rate is 100%. So you're doubling your money, all right? And let's say that we're going to compound every minute, all right? There's, if you're looking on page 340, no, let me get there in my book, 348, there's 525,600 minutes in a year, all right? So if I just look at this piece of the formula, 1 plus the rate raised to the time, we're going to see an interesting connection to something that you have already learned. So if I do 1 plus 1, my rate being, I'm doubling my money, right? 525,600 raised to the 525,600. This value is 2.718 and some more numbers, all right? This is an interesting number. If you do second ln in your calculator, it's E raised to a power. Let's raise E to the first power. And look what that value is, 2.71828. That's what happens. As your compounding period gets smaller and smaller and smaller, the value of your 1 plus rate, the rate to the time, approaches the value of E. All right, so we can have a compounding period that is defined annually in any time period. But as the time period gets smaller and smaller and smaller, we're approaching a continuous compounding, such that every second that interest is compounding. And when your interest is compounding continuously, then we're always going to use E. So the formula for continuous compounding, not exponential, because this is exponential, all right? This is continuous. So it's the amount over a period of time equals PE. We're going to raise E to the rate times time, all right? That's when we're going to use continuous, okay? So let's use this same set of facts and say, instead of compounding annually, quarterly, weekly, let's say it was compounded continuously, all right? And let's see how that changes our numbers. So the amount over, let's say 2 years, we're going to use the same 2 years. We use the same rate, 8%, equals the principal, 6,000, E, raised to the 0.08 times 2. And you always use years here, unless it's bacteria and everything is in days. And it gives you that rate, that daily rate. All right, so when we do this in our calculator, 6,000 times shift LN to the 0.08 times 2, I get just a little bit more. It's $7,041.07. That's the most you can compound, is continuously. And when we compound continuously, we're using the value of E. All right? Make sense? All right, so look at, let's just walk through some of these examples. All right, look at example 3. I am on page 347. It says if $5,000 is invested, that's my principal. So P is going to be $5,000 at an annual rate. So I know it's annual, and my rate is going to be 0.07, but it's compounded daily. When will the investment be worth $6,800? So the amount over some time, we want it to be worth $6,800. I don't know the time. That's what I'm solving for. All right, so I'm going to write the formula. This is like my Y value. All right, so it's $6,800 equals $5,000 times 1 plus the rate, but I have to make it a daily rate, 0.07 divided by 365, and I don't know the time. That's what I'm solving for. All right, always when I'm solving for an exponent, I'm going to logarithms. So I want to isolate this term. 5,000 is multiplied by it, so I'm going to divide both sides by 5,000. I can simplify terms that are multiplied. On the right-hand side, I'm left with 1 plus 0.07 over 365 raised to the time. And 6,800 divided by 5,000 is 1.36. Right now I'm going to write an equivalent log statement. So it would be log base. This is my base. 1. I'm going to just do what this is. This 1 plus 0.07 divided by 365. Well, I'm just going to leave it like this because I can actually enter this in my calculator because I'm getting a strange number. That's my bottom number. And my argument is going to be 1.36 equals T. All right, so how do I get this in my calculator? It's in math. Go down to log base, hit enter. All right, it comes up there. I'm going to put, this is going to be my base. 1 plus 0.07 divided by 365. And 1.36. Okay, so I don't know if you can see that, but see, I put that in my base. And then I just hit enter. And that's how many days, right? We're in days. So it's 1,603 days. But if I want to know years, I just divide that by 365 to get how many years. And it's like 4.4 years, right? That's all I did. Divide that by years. All right, that's example 3. Look at example 5. So it's on the bottom of page 348. If you invest $4,000, that's my original amount, $4,000 at 5%, that's my rate. Interest compounded continuously, I'm writing down. When I hear those words, I'm using PERT, P-E to the R-T. How much is the account? How much is in the account at the end of 3 years? So my time is 3. I just plug these values in. It's 4,000. E raised to the 0.05 times 3. 4,000 times second ln, 0.05 times 3. And it's 4,000. So the amount to 3 years is 4,647 and 34 cents. We like compounded continuously. All right, look at example 6. The world population in so I'm on page 349. In 1950, so it gives me 1950 is when X is 0. So remember, we don't use like our years as our exponents. We decide what year is 0 and we count up 1, 2, 3 from there. So X equals 1 would be 1951 and so forth. All right, so that's at year 0. We're at 2.5 billion. That's my original amount. All right, my original amount. Or my principal, right? But it's people, so it's really not principal. All right. And has been increasing at 1.85% per year. That's my rate. So the rate is, I move the decimal place to the left twice, so it's 0.0185. Write a function that gives the world population, okay? Well, the amount over time is going to be my original amount, 2.5 billion, times 1 plus the rate raised to time. Make sense? All right. Look at example 7. Now I'm on page 350. At the beginning of the experiment, that's the original amount. At the beginning of the experiment, that's my original amount. We had 1,000 bacteria. 5 hours later, that's my time. So now we're in hours. 5 hours later, so that's the amount after 5 hours. I have 7,600 bacteria. Assuming that it grows exponentially, right? Amount over time equals the original amount times 1 plus the rate to time. That's the exponential formula, right? That's not continuous. They didn't say continuous. Continuous growth. All right, how many bacteria would there be? So I want to know the amount after 24 hours. So I don't have the rate. All right, so now I need to solve for the rate. But I can use this information. I have everything here except the rate. All right, so I'm going to set 7,600 equals my original amount, 1,000, times 1 plus the rate, and it's 5 hours. So I'm going to get what this is, because this is going to be, amount after 24 hours is going to be the 1,000 times whatever this value is, right? That's what I'm solving for here. This is going to represent 1 plus the rate, and I'm going to raise it to 24 hours. Okay, so the first thing I do, I can simplify it. I want R by itself. So 1,000 is multiplied. I can divide both sides by 1,000. 7,600 divided by 1,000 is 7.6. It's 1 plus the rate to the 5th. Now, I can take the 5th root of 7.6. And I do that in math. It's number 5. 5th root, number 5. And I do the 5th root of 7.6. See what I did? Just the 5th root of 7.6 and hit equal. So what is this 1 plus R equal? It equals 1.5002. I'm going to leave that in my calculator. I'm just going to raise it to the 24th power. Okay, I'm going to take that. I'm just going to raise it to the 24th power. I'm going to hit equal. Then I'm going to multiply that by 1,000 times 1,000. And I get, that's what I get. It's a big number. 16,900,721 bacteria. Obviously, we knew it was growing exponentially, and that is pretty exponentially. 24 hours, that's 2 days. We go from 1,000 to 16 million, almost 17 million. All right, now we're going to go on to example 9, which deals with exponential decay. We've been dealing with exponential growth. And that happens when we have money, when we have bacteria, when we have like rabbits multiplying, anything that's growing exponentially, all right? Decay happens with radioactive material. And when we have decay, there's always a half-life. And there's a formula for this. It's on page 352. So when we have decay, all right, so remember, all right, if we go back to this little sheet, if we are growing exponentially, if that's the formula, if we're growing, then your base, this A value, is going to be greater than 1. And it has been. It's been 1 plus the rate, right? Raised to the time, all right? If we're decaying, if it's decaying or if it's, decreasing, then this A value is going to be less than 1. So it's going to be between 0 and 1. And that is the case with decay, with radioactive decay. Look at the formula. It is on page 352. So here's the function. It's the principal amount times 0.5, because radioactive material has what's called a half-life. And the half-life tells us how many years does it take to have half of that radioactive material left, all right? That's what half-life tells us. And we're going to be dealing mostly with carbon-14. All right, raised to the x, which is time. So x is going to be your time. And H is going to be the years of the radioactive material half-life, of the radioactive material half-life. Every radioactive material has a different half-life. Carbon-14 is 5,730 years. That's what you'll use the most. All right. So we're going to use this formula. We're expecting decay. All right, so look at example 9. When a living organism dies, its carbon-14 decays exponentially. So when it dies, it has 100% of whatever its carbon-14 is. But over time, that decreases. All right? An archaeologist determines that the skeleton of a mastodon has lost 64%. So he has lost 64% of its original carbon-14, which was originally, right, 100% RP, whatever that was. We don't know. Not P, but amount originally, right? Amount originally. Got it? They do use P here. Okay, that's the same thing as P. All right, so it's lost 60. So how much does it have left? Left is what? 36% of its original amount, right? That's what's left. 36% of its original amount. All right, the half-life of carbon, it tells us, is 5,730 years. That's the H value. So H is going to be 5,730 years. Okay, so we have no clue how much is left. We just know that 36% of the original amount is left. All right, so I'm going to write the formula. The amount left, which is 0.36 of its original amount, that's what's left, equals the original amount, right? You got it so far? Times 0.5 raised to the x. We don't know how long it's been since it died, over its half-life, 5,730 years. All right, got it? Make sense? I'm going to do the same thing to try to isolate this x. So P is multiplied by it. So I'm going to divide both sides by P. My P's eliminate. I'm left with 0.36 equals 0.5 raised to the x over 5730. All right. I'm going to logarithms. It's going to be the log base 0.5 of 0.36 equals x over 5730. I'm going to do this in my calculator. Remember, it's math. And I go down minus a. My base is 0.5. My argument, this is my argument, base, argument, exponent. 0.36 equals, so that's what it equals. Once I have that equaling, now I'm going to multiply by 5730 on both sides. And I've solved for x, so I'm going to take that and multiply by 5730. And that's the answer. That's how many years? 8,445.63. All right, does it make sense? It makes absolute sense, because after 5,730 years, I should have half left. 50% after 5,730 years. If I have only 36% left, it should absolutely be more than 5,730 years, right? So it makes sense that it's 8,445 years. Okay?